Hello and welcome everyone to this month's webinar. Go ahead and start with just a brief introduction to Connexus and go over a few housekeeping items before we get going with today's presentation. For those of you who are unfamiliar with Connexus, we are a process safety consulting engineering company that provides technical safety services for new and existing facilities. We provide a full complement of training, consulting, engineering services, and technical software. To learn more about our products and services, please visit connexus.com for more information, or feel free to reach out to me personally if you like. Our goal is to do one webinar per month, so please consider subscribing to our newsletter on the Connexus website so you're up to date about the timing and subject matter of our upcoming webinars. We also post webinar and other important information on our LinkedIn page, so please consider following Connexus on LinkedIn as well.
And we promise to only send you one email a month.
Yes, we are very conscious about our messaging and try not to overload people with that. So we promise not to send you a whole bunch of stuff every day. Also, so you're aware, this webinar is being recorded and will be available for viewing on connexus.com by the end of the week. We will advise when it's ready with a LinkedIn post and on our website. We like to keep these webinars as a conversational format, so if you have any questions along the way, please feel free to speak up, or if you prefer, type your questions into the chat section of the meeting. We want to make sure we get all your questions answered for you. With that, I'll turn it over to today's presenter, President of Connexus, Ed Marzell. Take it away, Ed.
All right, thanks everyone. Thanks for attending. Let me go ahead and share my screen. I'm going to share my whole screen because I jump around quite a bit as I'm going through the presentation. So we've got, we're going to start out in the PowerPoint slides, and then we're going to kind of move around into the internet and such. But just for your information, everything that you're going to be seeing is well, not everything that you're going to be seeing. I'm going to expand a little bit, but most of what you're seeing is going to be contained in the Connexus training class called Safety Requirement Specifications, which is available in our Process Safety Training Center online learning management system that's part of our Connexus integrated safety suite of software products for doing technical safety tasks. Today's topic, and it involves kind of the detailed design of safety instrumented systems, is looking at Energized-to-Trip versus Deenergized-to-Trip. What are the strengths and limitations of those two approaches? And then if you're going to use an Energized-to-Trip system, which shouldn't be a surprise to you, is not the favored approach, but it's an allowed approach. What are the considerations that you need to make when you're doing that type of design? So let me go ahead and jump into the course materials and the presentation materials. Again, this is section 8, which is related to the concept of Deenergized-to-Trip and Energized-to-Trip. So let's start off with, what do we mean by these things, Energized-to-Trip or Deenergized-to-Trip? So for a safety instrumented system, you're typically taking a measurement. That measurement needs to get signaled usually to a logic solver of some sort, whether it's relays or a programmable logic controller computer-based system that's going to accept those inputs, do some logical processing of those outputs, and then send a signal to a final element that's going to take some sort of action on the process. And the most common, probably greater than 99% of all final elements, are either going to be motor starters for rotating equipment. So pumps and compressors, you're going to send a signal to either turn them on or shut them off, usually shut them off, or a valve. And valves, probably of those two, valves are probably around 90%. So most of the time you're going to be opening or closing a valve to get yourself to a safe state. So when we say Energized-to-Trip or Deenergized-to-Trip, we're primarily looking at the signal in between the different subsystems of the safety instrumented system. So how does the signal get from the sensor to the logic solver and from the logic solver to the final element? So in a de-energized-to-trip system, let's say our sensor is a pressure switch. In a de-energized-to-trip system, the contacts on the switch are closed, allowing electricity to flow to the logic solver, and having a 24-volt DC signal, usually 24-volt DC, having that power applied to the logic solver means that the equipment under control is in a safe, normal operating condition. And then when you remove the power, and the logic solver sees that the power no longer exists, that's an indication that the system is in an abnormal state. Using the approach where you de-energize to trip, meaning you open the switch, you remove power from the logic solver to signal that there is an abnormal condition of the plant, that is de-energized to trip. De-energized to trip is the more favored approach because it is more resilient to dangerous failures. So the most common dangerous failure would be that you disconnect a wire. So if you disconnect a wire, simply disconnect the wire in a de-energized-to-trip system, all of the downstream components of the safety instrumented function will realize, or will basically be told, be informed, that we can no longer confirm that the process is in a safe state. Therefore, you must go to your trip condition. The problem with de-energized-to-trip systems, though, is that they have higher spurious trips. Anytime you lose power, anytime you accidentally lift a wire, you're going to shut down your plant. And sometimes these shutdowns can be more dangerous than the unavailability of the safety system itself. So you'll see in, for instance, fire and gas systems, when you're signaling a dry chemical system to spray dry chemical to put a fire out, that will be considered or be designed as energized to trip, because we don't want to accidentally spray all this chemical fire retardant agent in the air when there isn't actually a fire to put out. Now, what I've been talking about so far is specifically looking at the signaling systems, but there's also the bigger concern is at the final element itself. So if I need to make a valve go closed or I need to make a valve go open, I need some sort of motive force to make that happen. So think about a valve that is driven by a piston. So in an energized-to-trip system, what you would do is you would apply that pneumatic air, forcing the piston to move, forcing the valve to go to its normal position. And in a de-energized-to-trip system, on the other hand, you would use your instrument air to push the valve into the open position. And then when you remove the instrument air, the static maintained force of the spring is then going to push that valve into the closed state. So you have some stored energy that is going to be activated when you remove the signal. That's going to be the de-energized-to-trip system. All right, so that's kind of level setting, just giving you the overall description of what we mean by energized-to-trip versus de-energized-to-trip. De-energized-to-trip systems are also sometimes called fail-safe, because when a failure occurs that removes power, the process will move to the safe state. Now, we're all SIS engineers, so we know, well, some failure modes are safe, some failure modes are dangerous, even in a de-energized-to-trip system. But again, just a little bit of level setting on the concepts and the terminology. So now, as we go through this section of the training course, or through the webinar, there are three things we're going to do. First off, we're going to go into the standards, and I'm not just going to go into the most recent version of the standard, which is a little bit odd, and I will explain why. but we're also going to go historically all the way back to the early 90s when I joined the ISA 84 committee and talk about the discussions that we had before we released the first version of the first functional safety standard, which was the ISA 84 standard that was released in 1996, predating the IEC 61511 standard by 7 years. So we'll go into the standards requirements. Then we'll talk about designing Energized-to-Trip systems, because the standards are going to tell you that we prefer Deenergized-to-Trip system. There is a tacit assumption in a lot of the rest of the standard and a lot of the way that we do calculations and detailed design that assumes we're using Deenergized-to-Trip. So we'll go over all of those designs and the design requirements, and we will do that not only for the more common electrical systems, but we'll also look at the pneumatic and the hydraulic analogs to Energized-to-Trip. So here, when we say energize, we mean motive force of any kind, not just electricity. Then we'll close things out with going through a de-energize, Energized-to-Trip workflow. So when you're preparing your safety requirement specification that define the detailed design of your safety instrumented system, you will have kind of a workflow for what are the tasks that need to be performed to make sure that all of the Energized-to-Trip circuits are considered, documented, and designed properly. Okay. Let's start out with what the standard says, and there are a couple of requirements that we're going to get to that are in the most recent version of the standard. So we're going to start with clause 10.3. So those of you that are familiar with the standard know that 10.3 is the safety requirement specifications clause. It provides a laundry list of all of the things that you need to document about the design of your safety instrumented system. And one clause there says requirements relating to energize or de-energize-to-trip for each SIF need to be specified. Now, right out of the gate, again, I kind of start with my unhappiness of how the standard is written and how that clause is written. And we'll get into this later on. The choice of Energized-to-Trip versus de-energized-to-trip is not applied to the SIF. It's very possible that you can have an Energized-to-Trip sensor subsystem with a de-energized-to-trip final element and vice versa. So this discussion of energized-to-trip versus de-energized-to-trip actually needs to be done at a component level, not a SIF level. Furthermore, it might actually even be a general requirement if you choose to do everything exactly the same way. So there are a lot of companies that flat out say, well, I'm not going to use de-energize, or I'm going to use de-energized-to-trip for everything. I'm not ever going to use energized-to-trip. And at that point in time, you can make one statement in a general requirement that applies to your entire safety instrumented system. So this term it's true, but kind of remember that this decision is on a component by component basis, not a safety function by safety function basis. Okay, the next clause is the big dog, and there's also an informative note. This is from the 2016 version of the IEC 61511 standard, which is correlated, for those of you in the US, with the 2018 version of the ISA standard, which is 100% completely identical to the IEC standard. I think we're at that point pretty much globally, whether it's AS 61511, ISA 61511, BS 61511, around the world, we're pretty much all in the same place at this point in time. Okay, if you read the clause, it says, for any SIS device, whoa, they got it right in this clause where they didn't in the SRS clause. They're basically acknowledging that this design functionality, design feature is at the device level, not at the function level. Okay, so for any device that on loss of utility, loss of motive force, loss of power, loss of energy, and it goes through the example. So it's making very clear that it doesn't matter what my utility, what my motive force is, whether it's electricity, whether it's pneumatic air, or whether it's hydraulic oil, all of those are covered in this clause. So for any device that on loss of utility does not fail to the safe state, meaning that when you lose power, you're going to have some sort of stored energy like a spring that's going to force you back to the safe state. If that's not the case, so if you're energized to trip, then there are things you need to do. Loss of utility is item number 1. And then circuit integrity is item number 2. These are the 2 things that you need to look at. I need to know that I lost my utility, detect it, and put up an alarm. That's item number 1. Item number 2, if I lost my circuit. So if I dropped a wire, or if my pneumatic air became disconnected between the source and the valve, I need to be able to detect that's occurring and put up an alarm. So depending on what type of signal you're losing, that might be done with end-of-line monitoring, which is an electronic function that I will discuss in some slides coming up, or you might look at pressure measurement of your hydraulic or pneumatic supply to tell you the same thing. So if that happens, you have a dangerous failure, a dangerous detected failure, but a dangerous failure. As a result, you're going to need to take action in accordance with 11.3. So 11.3 is the clause in the standard that talks about what your response needs to be to a detected dangerous failure. And making a long story short, you either trip the plant out because you know that if you need to shut down, you're not going to be able to, or you take compensating measures. So you replace that failed component with a human being or another instrument loop or redundant equipment in the SIS. Some sort of compensating measure needs to take place until you're able to perform a repair of the failed component. Okay, so you'll see that there are 2 things. I need to detect an alarm, loss of utility, detect an alarm that I lost my circuit integrity. Now, there's an informative note here that says utility integrity can be improved through using a supplementary supply. So if I have a backup battery, an uninterruptible power supply, if my main power supply fails, I can switch to my backup power supply and everything is still going to work. Put up an alarm, and then I could go repair my power supply. And you can do the same kind of backup power philosophy on the pneumatics and the hydraulics by applying air reservoirs, hydraulic accumulators, and secondary sources of gases and liquids. Note number 2 says that loss of utility is likely to affect multiple SIFs and possibly multiple SISs. Therefore, you need to think about common cause. So if my instrument air compressor goes down, kind of getting a little bit crazy with my example, then if all your safety functions are energized to trip and you lose your instrument air compressor, none of your safety functions are going to be able to work because they all rely on that same compressor. So common cause failure is a big deal. Of course, I mean, in reality, if you lose your instrument air compressor, everything's going to shut down anyway, basic process control and SIS. So maybe not that relevant example. Okay, so this is the big dog requirement in 615.11, 11.2.11. This is what you need to think about if you make that decision to put in an Energized-to-Trip system. There is one more clause that is still in clause 11, which is the detailed design portion of the standard. And it says, Energized-to-Trip circuits shall apply a means to ensure circuit and power integrity. So once again, I get on my soapbox and say, okay, well, you already told me this in clause 11.2.11. Why are you telling me the same thing again? And it even refers back in this note saying additional requirements for loss of power in 11.2.11. Whatever. There's nothing wrong with repeating other than annoying people with repeating the same stuff in multiple portions of the same document. The other thing to note here is, well, obviously note one, an example of means to ensure circuit and power integrity is end-of-line monitoring. I'm going to have a slide where I'm going to show you what we mean by end-of-line monitoring, how it's done. Usually it's done for you by your equipment vendor. Just, you flip a bit in your configuration. It's possible to do manually, but man, is it tough to do. I will explain when we get into that. Okay, so for end-of-line monitoring, what's basically happening is you're going to have a pilot current that's continuously monitored to detect the circuit continuity. So if you have a 24-volt DC circuit, instead of applying 24 volts, you'll apply 2 volts or 3 volts. And you can measure that 3 volts exists, but it's not enough to drive that final element into its active position. So we're trickling a little bit of power through, enough to know that I haven't lifted any wires, but not so much that you're going to activate your final element. That's what we mean by end-of-line monitoring, also called circuit integrity monitoring, also called trickle current. That's one of the approaches, and we will get into that. Now, let me back up a little bit. So right now, I'm going to jump out of my presentation, and I'm going to go actually into the standard. All right, 11.2.11. What you're seeing on the screen here is exactly what was on that slide that we were just looking at. For any device that on loss of utility doesn't go to the safe state, you need to, 1, detect and alarm loss of utility, and 2, detect and alarm circuit integrity. And then there's an informative note about the fact that if you use a backup power supply, that's better. Now, the next tab over here, I'm going to go to the OG, which is ISA 84. So this is the version of the standard that started it all. This is the one that was released in 1996. And back in the day, we had clause 7411, which said Energized-to-Trip discrete input-output circuits. So we were only looking at the I/O circuits and only looking at the electrical aspects of it. Obviously, you can see we've expanded in the more recent versions. But we said Energized-to-Trip input-output circuits shall apply a method, end-of-line monitoring, such as pilot currents, to assure circuit integrity. So all that we were worried about is item, I believe it's item 2, which is that we lost integrity. Somewhere a wire got disconnected, and now the Energized-to-Trip circuit is not going to work when we needed it to work. So we published this back in 1996. And, as the world came back and started providing improvements and comments to the standards, we said, well, hey, what about pneumatics? Hey, what about hydraulics? Hey, what about backup power supplies? Hey, what about alarming to let us know that we've lost circuit integrity? Now, granted, alarming is kind of implied in here, but the power supply is not. So this is the first pass. Then we moved to here is the 2003 version. So this is what was released in 2003 in IEC 61511. And it's an improvement over the original ISA standard. It says, for subsystems that don't fail to the safe state, all the following shall happen. So we still have loss of power being detected. That's number one. We still have loss of circuit integrity. That's number two. But in 2003, the standard was more stringent. It didn't have an informative note saying, maybe you should think about a backup power supply. It straight up said, thou shalt have backup power supply if you're using Energized-to-Trip. Wow, we have violated all laws of government and standards by making something less stringent instead of more stringent. Usually, you add more laws and never remove any of the existing ones. This is so bizarre. So what the heck happened between 2003 and 2016 that got this requirement whacked and replaced by an informative note saying to think about having it instead of demanding that you do it? And the answer is, in some cases, a backup power supply is not really feasible, not really realistic. So if, for instance, you're using 240 volt three-phase power to move a motor operated valve, a backup supply of three-phase 240 volt power is expensive and tricky to engineer at the very minimum, as opposed to an additional 24 volt power supply is a trivial cost. And, you know, with a bridge, it's not really that hard to install. It's kind of easy to do. So IEC 65 committee, which I am on now, kind of walked back the requirement for a backup power supply and said, well, let's put in a note saying that you should think about it, but we're not going to actually demand that you do it. So that's kind of a curiosity to me, one of the rare instances where you'll see a standards committee go full bore on something and then get pushback from industry and walk it backwards. All right, back into the presentation slides. Looking at the key attributes of Energized-to-Trip versus Deenergized-to-Trip system, I already went into detail on a lot of this when we were on the first slide. So the first thing that you want to think about doing, requirement number one from the clause, is you want to alarm on loss of power. So this is exceedingly easy to do for an electrical system. If you have power and then you lose power, that's easy to detect with a relay-based system as an input to a safety PLC. Knowing that you've lost power is one of the most trivial and easy things to be able to detect. So if you lose voltage in a digital input, that's something that you'll be able to detect, and then you're going to want to generate an alarm. And that alarm you can enunciate through a myriad of different methods, through the basic process control system operator interface, through a dedicated SIS interface, light boxes, you name it. We just need to have an alarm saying that my SIS power is gone, so I am not going to be able to go to a safe state if I need to. That same loss of power, though, for pneumatics and hydraulics will instead be a pressure alarm. So if I've got a typical instrument air supply of 20 psi instrument air, and I need that to be able to force a valve to go to the safe position, if I get a loss of power, I'm going to get a loss of pressure. The pressure is going to go away. So whether you want to measure that with a pressure switch sending a digital signal or a transmitter sending a 4 to 20 milliamp, it's all up to you. But basically, you're going to be looking for the pressure of that pneumatic or hydraulic component, and you're going to want to take that measurement as close to the final element as possible. There's a possibility that if you have downstream leaks, you won't be able to detect that if your pressure measurement is located too far upstream. We'll have a kind of a symbolic, simplified P&I showing you the concepts of where some of these things should be located. All right. The next item is number 2 from again, the 61511 standard current version, and that's circuit integrity monitoring. So we need to be able to detect if I disconnected a wire, but you also need to be able to detect if you disconnect pneumatic tubing, hydraulic piping. Anything that conveys a signal, whether it's electrical or pneumatic, if it gets detected, we have to know about it. And now going back to the pneumatic side, it's again pretty easy. If you open up your instrument air tubing, you're going to blow all your pressure out, and you're going to be able to detect that with a pressure alarm, whether that's pneumatics or hydraulics. It's a little bit trickier with electrical systems, because how do I know that I don't have power if I never have power? How do I know I'm not going to have power if I never have power there? So you need to use circuit integrity monitoring for electrical circuits so that you do have some sort of power all the time. So that's going to be a trickle current that you're going to configure. Now, if you have a sophisticated logic solver, so your big brands out there that are going to have SIL 3 certified safety logic solvers, usually this is a configurable option. You'll be able to look at an input circuit, you'll be able to look at an output circuit, and when you're configuring it, you can put a checkbox to say that there's circuit integrity monitoring, or it's a verified. It goes by a bunch of different names, but the logic solver vendor will do all of the engineering for you in terms of applying the trickle current when the circuit is de-energized, and then also being able to detect the presence of that trickle current. Now, it is theoretically possible to bolt on a trickle current, but it's extremely tedious, it's extremely difficult to do, and it can often result in a lot of false positives and also nuisance trips. So the bad news is, if you have an old 1980s, 1990s vintage commercial off-the-shelf PLC that's operating a compressor that has Deenergized-to-Trip circuitry, or I'm sorry, Energized-to-Trip circuitry, because it's very old, and you want to try to bolt on the circuit integrity monitoring to that ancient PLC, the bad news for you is it is a nightmare engineering project to have to do this, and I do not envy you, but theoretically it's possible. Now, item number 3, which was included in 2003, but then whacked in 2016, and now it's just kind of a maybe you should think about it informative note, is that concept of the backup power supply. It is no longer required in 2016. It was required in 2013. So I would always recommend that you apply it if it's feasible, but then I will always acknowledge that there are situations where it might not be feasible to do, like a high voltage 3-phase power to supply that's driving a final element. That, kind of gets tricky to manage that kind of thing. Okay, so let's take a look. I said I'd give you kind of a simplified view of these different systems. So what I'm showing you here is kind of a loop diagram view, or kind of an old school loop diagram that contains all the components of an Energized-to-Trip electrical circuit. So this is our ETT circuit. So you'll notice that for this circuit, so I have a switch in. So right now, this is just an input circuit. Okay. And I have a switch out in the field, and this switch is normally open. So normally open, normally closed is going to be your shelf state. So when you don't apply power, what position is the contact in? So in an Energized-to-Trip circuit, the switch is going to be open, and you're going to close the switch to apply power when there is a dangerous condition. So when the process is in its normal operating state and there is no hazard, the normal condition, there are 0 volts on the return, 24 volts on the send, because the switch is in the open position. Okay, now, key aspects of the design. First off, I'm showing you 2 power supplies. So I've got power source 1 and power source 2. I'm supplying power from an uninterruptible power supply, and I have a 24-volt DC power supply device that's generating power, and it's going to send that power through what I didn't draw my Wheatstone bridge in here to resolve or is it a Wheatstone bridge? My bridge to resolve the fact that I've got power coming from 2 different locations. Now, so this is power supply 1, and power supply 1 is going to have an alarm associated with it. So I'm wiring in a voltage alarm low, telling me that I've lost voltage on the A power supply, and I will do the same type of measurement on the second power supply. So this is for the power supply as a whole. It doesn't need to be done for every circuit that uses the power supply. So only once per power supply do you need, in this case, we're going to have a digital input. The way I've drawn it, it's local, but you can have it wired in through your DCS however you want. Okay, so that kind of is item number 3. Item number 3 is the dual power supplies. Item number 2 is the alarm indicating that I've lost the power, and that's going to be separate and distinct for each power supply, is a best practice. You could alarm off of the combined signal, but that's not going to achieve our objectives. We want to be able to detect and repair out without generating a dangerous condition. Okay, so now I have the power coming into my SIS logic solver. The logic solver is then going to distribute that power out to the field. So what we're looking at here is one channel. This is one channel going to the field switch. As you know, the SIS logic solver output cards are probably going to have 8, 16, 32 channels on them. This is just one of those channels. Now, the thing to remember is that there is a trickle current, and then I'm going to draw in here something called signal current. So I can have my signal drive the voltage going out, or I can have my trickle driving what's out to the field. And kind of to make this a little bit clearer, let me kill field switch and just say SOV coil. So that makes things is going to make things a little bit clearer here. So in the SOV coil, things will be a little bit different because I'm not always applying the full power. I'm going to be applying a trickle current. So a trickle current, instead of 24 volts, would be something like 2 or 3 volts. So when there isn't a dangerous condition, the logic solver will be sending 2 to 3 volts and receiving the 2 to 3 volts. And hopefully that those 2 to 3 volts are not going to be enough to create enough magnetism in the SOV coil to pull it in, but enough for the system to know that there's a failure. So now you're going to see 2 to 3 volts going out. You're going to see 2 to 3 volts coming back in. When I get a dangerous condition, so now let me switch to red. So now let's say the wire became disconnected out in the field right here. I still have 2 to 3 volts on my input, but now I'm going to see 0 volts on my output. And then the logic solver is going to know that I'm supposed to have 2 to 3 volts coming back. I have 0. Something bad happened in the field. I need to open this up. Okay. Also in this configuration, if the logic solver says I need to activate it, This signal current is going to give me 24 volts. Maybe I should go with a different color here. So let's say my third case is when things are active. So when I want to activate my safety function, I'm going to apply 24 volts here, and then I'm going to get something less than 24 volts coming back because I've got some impedance through my coil. Okay, so that's kind of the configuration of how this works. And all of this concept of sometimes I'm sending a signal current, sometimes I'm sending a trickle current, and when I'm sending a trickle current, I'm expecting a trickle current back. When I'm sending a signal current, then I'm expecting the full current back. All of those diagnostics are things that your logic solver vendor is doing for you, and you can turn it on with a simple flip of the switch. If you wanted to do this as a bolt-on, then the PLC is only going to do what's in green, that signal current. You're going to need to then apply this trickle current externally. So you're going to need to have this trickle current that you're going to need to put on the wires right there on the terminal strip outside of the logic solver. And you're also going to need to take the voltage measurement to see what's coming back to make sure your trickle current is actually flowing. So as you can see, there's a decent amount to what we're doing here. And if your logic solver isn't providing it for you, it's not going to be impossible, but it's going to be pretty tricky for you to do yourself. Okay, so that's kind of your electrical circuit. Let's look at a pneumatic supply. So one example of, you would say, well, why would you want to do this? So some of you are in refining. So in refining, we have a process called the hydrocracker. And there is a situation where you will want to depressure the hydrocracker because the reaction's running away. So the temperature starts to skyrocket. And if we don't blow all of the hydrogen out of the hydrocracker, we're going to overheat this. The external piping is going to melt. You're going to have a massive jet fire, which is probably going to result in multiple fatalities. Now, so we have a safety function that's going to measure the temperature. We're going to go into our SIS logic solver, and that is going to activate our solenoid valve, which is going to bring our process to a safe state. Now, most hydrocrackers have a fail closed valve, meaning when there's no energy applied, it's in the closed state, which means it's going to be air to open. So I need to apply instrument air to make it go open. And to get to a safe state here, I need to open the valve to depressure. Yet most of the time, I'm failed close, which means the final element subsystem portion of this circuit is Energized-to-Trip, air to open valve for a depressuring valve. Why would I do such a thing? Well, you've got roughly 2,000 psi of hydrogen and hydrocarbon in this vessel. If I were to accidentally open this valve, you're going to send all this stuff to the flare header, and you're going to get a flare that you can see from outer space. This is not a trivial event. So just the flaring is going to be massive and crazy. Furthermore, this hydrocracker vessel has to be immune to a lot of corrosion mechanisms. Therefore, you need exotic metallurgy in the reactor. And you don't want to build an entire thick-walled vessel out of exotic metallurgy because it's expensive. So instead, you create a thin coating on the inside, a cladding of your exotic metallurgy, and then you go back to your basic carbon steel for the outer shell. Well, what can happen when you depressure a lot? Maybe not the first time, maybe not the second time, but over time, your hydrogen, so outside is your cladding and here's your carbon steel. Your hydrogen is going to penetrate in because it's a super tiny molecule. Then when you want to depressure, all the hydrogen that's back here in the carbon steel tries to go back into the reactor simultaneously, and it pulls the cladding off. When you pull the cladding off, now you're exposing parts of the reactor directly to the process material, and you're going to compromise your entire vessel. Therefore, depressuring, inadvertent activation of this function is a big deal. We don't want to do it. So even though we might have Energized-to-Trip circuiting for this electrical circuit, we're going to use an air to open valve. So now, what are those three attributes that we want for our Deenergize-to-Trip system? They were alarm on loss of utility. All right, so what's our utility in this case? Our utility in this case is our instrument air supply, 20 to 60 PSI of instrument air to put onto, I'm showing this as a diaphragm actuator, but it's probably going to be a piston. So we're going to want to put that air onto our piston to overcome the force of the spring that's holding it closed and make it go open. So the utility is the instrument air, and I can detect that I lost my instrument air with this pressure alarm low. So whether it's a pressure switch or a pressure transmitter, you might enunciate it at a local alarm panel. Right now, we've got it drawn as a control room alarm panel. In the DCS, however you want to do it, all the options are on the table for you. So that's how you're going to know that you lost utility. Okay, the other part is circuit integrity. And here is where you learn that not everything is 100%. So when we say loss of circuit integrity, what we're saying is that, well, if we get a disconnection, let me switch back to a red pen here so I can bring this concept home. So if we get a disconnect in the tubing right here, or a disconnect in the tubing right here, we're going to know that we lost that tubing because you're going to blow. So you're just going to blow all your instrument air out of that hole, and you're going to get a pressure alarm low. That tells me that we lost our circuit integrity. But now we're going to realize that this isn't 100% because this solenoid valve is basically going to be blocked here. So if we lost circuit integrity here, there's no air pressure here. There's no way to know that you lost pressure on that side, which is why you're going to want to make sure that that segment of tubing that's not protected by your circuit integrity monitoring is as small as possible and routinely inspected on your car seal program or your mechanical integrity program to make sure that it is still operational. Now, possibly you could also have a disconnection on this side of the instrument air supply, or I'm sorry, on this side of the check valve, but that's not going to prevent your safety instrumented system from working. And the reason it's not going to prevent your safety instrumented system from working is because we have the third, which is optional, and that's backup power. So in this case, our backup power is going to be held in this volume bottle. You should size that volume bottle to be able to move the actuator 3 times. So for those of you that are not familiar with volume bottles, there's going to be kind of a diaphragm with a spring. And when you bring instrument air in, it kind of pushes this diaphragm down. or piston. It kind of pushes the piston down and gives you that full air pressure inside that vessel. And then when you lose pressure downstream, that spring is going to force that piston back up to give you more pressure and kind of push that air downstream into the system. So that's how a volume bottle works. You'll also notice that we're going to include this non-return check valve upstream of the volume bottle. And that's because what we don't want to have happen is if we lose our supply pressure, we don't want the volume bottle to send all of its air backwards into the broken instrument air header. We want to keep it right here near the actuator for how it works. So this is typically how you would design an air-to-open valve or an Energized-to-Trip final element system. I've drawn it out as pneumatic, so instrument air, but if it were high pressure pneumatic oil, basically everything is exactly the same, except you're handling oil instead of handling air. Okay, so those are the aspects of how you design an Energized-to-Trip versus Deenergized-to-Trip system. Now I'm going to kind of get into the workflow. And again, I'm going to be hinging on the Connexus tool for performing safety requirement specifications, which is our Vertigo software application. But the concepts that I'm talking about are going to be applicable regardless of whether you use someone else's software for SRS or if you're even doing it on, paper, Word files, PDF documents, what have you. Now, generally, you're going to prepare a general requirement that explains that you're going to use Deenergize-to-Trip for everything. So in the Connexus Vertigo software, we have a section where you input general requirements that are applicable to every instrument, every SIF, every portion of the safety instrument and function. So you can say something once instead of having to repeat it dozens or hundreds of times. So if you're a lucky one and your plant doesn't have Deenergize-to-Trip functionality, you can just say it one time, everything is Deenergize-to-Trip in a general requirement, and you're done. But you might want to say in your general requirement, you might want to leave yourself some wiggle room to put in an exclusion and say, if we run into deviations from Deenergize-to-Trip, they're going to be described in the notes or what have you. So you have the ability to give yourself some wiggle room to point to other locations. So that's one option, is the general requirements. Other options are to go to data sheets. So this is something that you can document on a data sheet by data sheet by data sheet basis. And so you don't mention anything in the general requirements, and you set up your data sheets to include that in the data sheets. And I'll show that. Actually, let me show that to you right now. So let me jump out of here, and I'm going to jump back into the web, and I'm going to show you a little bit of KISS. So Connexus Integrated Safety Suite, kiss.connexus.com. I'm going to go in with my single sign-on. I'm going to make the screen big enough for human beings to be able to read. I'm going to switch to my Connexus account instead of my ISA instructor account. And then I'm going to jump in. So I'm going to show you an example. So General Oil and Gas Operating Company is a fictitious facility that we use to do demos. Sorry about that. General Oil and Gas, Texas City Gas Plant, separations area. Okay, here's my SIS design basis. So in the safety requirements specification section, the way we have things laid out is there's going to be a requirements section and then a cause and effect diagram section. So I'm going to open up the requirements section. All right, so here you see kind of the list of those general requirements. So I can't remember where our general requirement for Deenergized-to-Trip was. One function. Okay, right here. This row you see contains the general requirement, and it also gives an exclusion. Now, we also have the ability to give data sheet for every IPF, a data sheet for every sensor, logic solver, and final element. So when I go into sensors, I can open up, and do I have any switches here? Let me just show you a typical data sheet. So this is a typical data sheet, and what you can do is you could put the description of what to do on Energized-to-Trip versus Deenergized-to-Trip as one of the items in this data sheet. So the way we have things set up is there is a response to fault field. There's a bad PV trip action where you can put the information in that describes how you're going to respond. So that would be a simple matter of going into the settings, customizing the data sheet for how you want to document this. So for my data sheet can be customized. So for a sensor, I can go into the input details and I can add information about loop power. I can remove information about loop power and add or remove the information related to Energized-to-Trip status, Deenergized-to-Trip status, and how the item responds. So it's completely up to you what format you want to use to do the documentation. Most people go with general requirements, but if you do have a lot of Energized-to-Trip, you might want to put that on your data sheets for every sensor. So as you're going through your workflow, regardless of your plant, you need to, as you're doing your SIS design basis engineering, you're going to want to review all of your inputs and outputs. So part of the workflow is to look at your IO list. For every input or output, ask yourself, look at the spec and say, is this Energized-to-Trip or Deenergized-to-Trip? If it's Deenergized-to-Trip and it's consistent with your general requirement, you're done. If it's Energized-to-Trip, then you need to make sure that the Energized-to-Trip functionality has been documented in the SRS. And you may also need to review other documents like your P&IDs to make sure additional piping like volume bottles have been included in that design. So with that, that is kind of the overview, the concepts of Deenergized-to-Trip versus Energized-to-Trip. We talked about the requirements from the standards, and we went all the way back to 1996 to see how they've evolved over time. We went into how that circuit is actually designed, and we did that from an electrical side, and we also did it from a pneumatic hydraulic side. Then we went back into the workflow. How do you document this in the SRS? How do you set up a program or an engineering process to make sure that it always gets considered and always gets documented properly? So with that, that is all that I have for the core presentation. And now I'm going to go ahead and turn the floor open to questions if anyone has questions.
Oh, hi there. Yes, this is Nirav Choksi. Thanks, Ed, for excellent presentation as usual. I've got a question about doing the PFD average calculation for Energized-to-Trip. And where do you stop basically in terms of, because for example, take example of power supply or instrument air, the failure mode of the system that's applied could be quite so. At what point do you say the upstream system is always going to be guaranteed, and therefore you only take account of the failure of like the two power supply modules, or indeed any other relays that come into it?
That is an excellent question. So if we go, let me actually jump out of the presentation, and we'll start by going back into the standard to take a look at what the standard says. So I want this one. So in terms of doing your SIL verification calculations, you're going to be in clause 11.9. 11.9 talks about your SIL verification calculations, quantification of random failure. So we want to verify that we have achieved or exceeded our target failure measure. with our calculated failure measure. All of this needs to be done by calculation. So how do we do that? 11.92 says we need to look at, and I could spend probably an entire webinar talking about random failures versus systematic failures and why we focus on random failures in these calculations. But the clause 11.92 gives you, it doesn't tell you how to do the SILCalc per se, but it tells you what attributes of the design you are required to consider when you do the calculations. So we start out with the easy ones, your architecture, failure rates that are dangerous, failure rates that are dangerous and undetected. So dangerous detected, dangerous undetected, dangerous never detected is B, C, and D. We need to consider the susceptibility to failures from the proof test, to common cause, how often we do our periodic tests, the coverage of the periodic tests. When we have detectable failures, how often or what is the repair time? This is going to come into play. Communication processes, this is going to come into play. K is not so much here. And then L. So the ones that I've just highlighted, I, J, and L, all of these are factored into Energized-to-Trip system failures. So when you lose a utility, so if I need electricity to move a valve, if that electricity is not available, it's going to be, it needs to show up as an unavailability. So what is the fraction of time that it is unavailable in comparison to the mission time or the test interval? So what is that fraction? That's an unavailability that needs to be included in your calculation. So how do I determine that unavailability? Well, it's, unavailability is downtime over uptime. So downtime divided by total time. And that, again, there's some simplifications in there. So you need to know this. So what's the mean time to repair for your utilities? What's the mean time to failure for your utilities? Those need to be factored in your calculations when you're using Energized-to-Trip. And this can lead to some complexity from item A, architecture, if you have backup power supply. So you might have, for lack of a better word, a 1 out of 2 voting arrangement, but it's more of a an AND gate in a fault tree that says, I will not be able to apply signal power if my main power supply has failed and my backup supply power has failed. But the standard clearly says you need to consider availability, reliability of your utility. It says you need to consider your repair time, because that repair time goes right in here is the top of the unavailability equation. And this J1 is estimated dangerous failure rate of communication processes. So if an Energized-to-Trip circuit loses its ability to act for 2 reasons, one is that you lost your utility. The second one is that you lost your signal. So an estimated rate of how often I disconnect wiring, and can I detect that, and how often or how quickly can I repair that, that all needs to get factored into the calculation. So the bad news is you really need to calculate all this stuff for Energized-to-Trip circuits. And most canned SIS software doesn't have any slots for you to fill in to do this calculation. So that generally means you're going to have to dump everything back out to a fault tree that's got a little bit more flexibility in modeling. The good news, though, is, as you've probably learned in an SIS engineering course, and I'm speaking now not just to you, Nirav, but to everyone listening, is that the least significant term in your overall probability of failure on demand is usually dangerous detected failures. And if you did an appropriate design and met the requirements, all of the failures that we're talking about for the Energized-to-Trip systems are dangerous, but they're also detected. So a dangerous detected failure is going to have a short mean time to repair, because your mean detection time should be a matter of less than a second. Honestly, in less than 1 second, you should be able to detect that you've either lost your utility or lost your communications. And then repair time, well, that could be tricky. You might need to repair a compressor. That could take a long time. You might need to just swap out a power supply, which could be done in a matter of hours. So because the dangerous detected term is the least significant term, as long as you have the ability to repair these ETT failures quickly, that PFD contribution should be vanishingly small in comparison to your common cause term, your dangerous undetected term, and your dangerous never detected term. Does that answer the question, or did I get sideways?
No, I think you did. You did very well. Actually, much better. Yeah, no,
All
thanks,
right.
thanks, Ed.
Sure, no problem.
We got a question here in the chat. It says, where do we get Energized-to-Trip reliability data for using failure rates for Energized-to-Trip components? And part 2 is, our SIF software does not allow Energized-to-Trip for SIL 2 and SIL 3. Does the standard specify or recommend the same?
Okay. All right, let me start with the last part because it's freshest in my mind. There is no restriction on Energized-to-Trip and SIL. So you can use Energized-to-Trip for SIL 2, you can use it for SIL 3, you could technically, there's no restriction in 6.15.11 even for using it for SIL 4. Now, I've got a whole laundry list of reasons why you shouldn't use SIL 4 for anything, let alone an Energized-to-Trip circuit. But the only thing in the standard, I showed you every clause in the 6.15.11 standard that talks about Energized-to-Trip versus Deenergized-to-Trip. There was no reference to restrictions based on SIL in 6.15.11. Now, I would be interested to know, and if you want to put it in the chat or you want to send me an email privately, what equipment vendor is preventing you from using, or software vendor is preventing you from using Energized-to-Trip for SIL 2 and SIL 3? I would be very curious to hear that, because that doesn't really make any sense to me, but that's maybe a discussion for another day. Now, where do you get the data? That's an excellent question. And the reality is that data is rare to completely unavailable. If you look at data for Energized-to-Trip components, so a solenoid valve used in an Energized-to-Trip circuit is going to have a completely different failure profile from one that's used in a Deenergized-to-Trip circuit. A lot of people simply want to take data from a database and invert it. And they'll say, okay, well, if my lambda D was 10 fits and my lambda S was 90 fits, if I switch to Energized-to-Trip, now my lambda D is 90 fits and my lambda S is 10 fits. Absolutely not. False, not true, completely unacceptable. You have to remember, for a solenoid valve that's in a Deenergized-to-Trip paradigm, it has power flowing through it all the time. So it's hot all the time. It has accelerated failure modes because it's hot all the time, and the primary failure mechanism of a solenoid valve is coil burnout that's going to lead to reduced magnetism and cause a spurious trip. So an Energized-to-Trip solenoid valve is going to have a much higher failure rate than one that's Energized-to-Trip because it's hot all the time, but it's also going to have a much lower safe failure fraction, because if your solenoid valve isn't energized all the time, then you're going to tend more to dangerous plunger failures as opposed to safe coil failures. So actually, you can't basically say, well, this is the data for a solenoid valve, and I'll just kind of change the numbers around depending on the application. That is absolutely false. You need to have a data set of Energized-to-Trip pieces of equipment. And once again, the bad news, that data is scarce to non-existent. So I'm sorry, did I answer both questions, or did I only answer the second one?
No, you answered both. Thanks.
Okay, perfect.
Yeah.
I don't see any other questions out there. Does anyone have anything else?
Eddie, it's Marcelo from Brazil. How are you?
Marcelo, good. Bom dia. Bom dia.
Bom dia. Bom dia. Okay. It's possible I put one valve or mechanical or pneumatic for resolve this problem?
Okay, is it possible to have a mechanical
Or pneumatic?
a mechanical or pneumatic
Yes.
from the HAZOP? Okay.
In case of the valve.
Yeah, oh, absolutely. So on the valve, ultimately, we need some sort of mechanical energy. So springs are usually used to apply mechanical energy. But when we have a spring return system, we generally consider that to be fail-safe. We generally consider that to be de-energized-to-trip, because we consider a spring to have excessively low failures, inherently safe. Now, the reality is springs can break too. So even in that type of mechanical through a spring system, if the spring breaks, you're not going to be able to get to a safe state. But absolutely, we do rely on mechanical systems, even in what we would call an Energized-to-Trip system. And again, for pneumatics, we treat almost exactly the same way as electronic.
Okay, understood.
Very good.
Okay, anything else?
Thanks again for all your time. I really appreciate your time and attention.